In order to formalize the concept of determinism, the French mathematician Pierre-Simon Laplace postulated an intellect now referred to as Laplace's demon. Laplace's demon has three properties. 1. Exact knowledge of the laws of nature. 2. Complete knowledge of the state of the universe at a particular point in time. Of course, Laplace was writing in the days before knowledge of quantum mechanics and relativity. And 3. The ability to solve any form of mathematical equation exactly. Except for extremely rare cases, none of these three conditions is met in practice. First, mathematical models generally provide a much simplified representation of nature. In the words of statistician George Boggs, all models are wrong, some are useful. Second, reality can only be assessed through measurements which are prone to measurement error, and which can only provide a very limited representation of the current state of nature. Third, most mathematical models cannot be solved analytically. We need to approximate them and then implement their solution on a computer, leading to further errors. At the end of the day, we might end up with a perfectly deterministic piece of computer code with relatively little correspondence to the evolution of the natural phenomena of interest to us. Someone approaches you, offering to play a game. They will repeatedly flip a coin. Each time it lands on heads, you win. Tails, they do. Of course, you both wage money on your bets. Let's call x1 the result of the first throw, x2 the second, and so on and so forth. We might formulate the following hypothesis. Each throw does not influence the others, they're all independent events. But they all share an underlying likelihood of winning, since the coin stays the same throughout the game. If presented with an impossible sounding streak of losses, drowning in bitterness at the loss of all your funds, you might begin to question whether the coin you were presented with is fair or not. You would be implying that there exists a certain value, let's call it P, between 0 and 1, that drives whether the coin lands on heads. The probability that the coin does so. In the case of an unfair coin, P would be closer to 0 than the 1/2 expected value for a standard coin. A great deal of controversy in statistics arises out of the question of the meaning of such quantities. Definity argues persuasively that one need not assume the existence of such things. Sometimes they are just assumed to be undefined properties of the experimental setup, which magically make the outcomes behave according to our probability models. Sometimes they are defined in terms of the sequence of observations themselves, such as limits of relative frequencies. This last is particularly troublesome because the sequence of observations does not yet exist, and hence the limit of relative frequency cannot be a fixed value yet. In another reality, the frequency of heads could, for example, oscillate between two values. Theory, of course, predicts that it converges, and empirically, you agree as you begin to lose count of your number of losses. But that's only because we fed into the theory a sensible model, which we could easily draw from your misadventure. You really shouldn't have agreed to play. So far, we've encountered two problems. One is the existence of a model that only depends on a single or few parameters. That's what we've done. The independent extends with a common value for P. But in more difficult situations, how is one to choose a model? We have assumed that probability distributions represent our or someone else's opinion about unknown quantities. At least a little thought should be given to how those probability distributions are chosen. The most common method for choosing a probability distribution might be called availability. Most people who study statistics formally for no more than one academic year will only be able to describe one parametric family of distributions suitable for use with continuous data. Other methods for choosing probability distributions are based on data analytic techniques. Either the very data on which inference will be based or seemingly relevant data are analyzed by various graphical techniques, hypothesis tests, or other procedures in order to try to select an appropriate probability model to use as a description of the uncertainty surrounding the data. The most direct methods for selecting distributions are those based on elicitation. In such methods, an expert, a term left to be undefined, is questioned about his or her beliefs concerning relevant random quantities, and a probability model for those beliefs is inferred from the responses. It's pretty funny to see that a discipline that houses axioms, theorems, and algorithms has also to deal with human psychology. Elicitation as a technique is justified upon the supposition that an expert's input should allow the statistician to whittle down the vast planes of the possible down to a few models to choose from. For instance, if they believe a quantifiable phenomenon has as much of a probability to be greater than its average as to be smaller, one might choose to work with a symmetrical distribution. All of this is to avoid the issue of misspecification, where the model doesn't correspond to the physical experiment being run. The formulas break down and the outputs become rubbish. Proposing a distribution on the unknown parameters of a statistical model can be characterized as a probabilization of uncertainty, that is, as an axiomatic reduction from the notion of unknown to the notion of random. More fundamentally, a probabilistic model is most often nothing but an interpretation of a given phenomenon, as opposed to an explanation of it. Therefore, the representation of an unknown phenomenon by a probabilistic model at the observational level as well as the parameter level does not need to correspond effectively or physically to a generation from a probability distribution, nor does it compel us to enter a superdeterministic scheme fundamentally because of the non-repeatability of most experiments. The probabilistic representation of partly explained phenomena should be perceived mainly as a simplifying but efficient tool conveying and quantitatively analyzing these phenomena. This perspective is really similar to the way physics can be seen as an interpretation of the world, and is a tool efficient enough to allow for a better understanding of this world, and incidentally, for technical progress, while not needing to correspond to a truth definitely unattainable. Now, if we want to actually solve the question of the value of p for the coin we've been presented with, there is one way. At this point, it might seem unsurprising that with the definition of what a probability is, we can recover p by averaging over the observations we've made. Another way of seeing things is that we've built the theory to validate what we would have instinctually done. However, we arrive at a schism. While we've covered the classical frequentist solution, we could have done things differently. In Bayesian statistics, you model p itself as random. This means that rather than trying to reach a real value that exists in the world, you try to determine a distribution that summarizes your belief in the value of p. To inform this belief, you of course use the result of the experiment, but also the belief or uncertainty you held before the event. This is called a prior distribution, while the final one is called the posterior. For the record, the computation you go through to get from the past to present beliefs is called Bayes' law. From a philosophical point of view, it is generally agreed that knowledge stems from a confrontation between a prioris and experiments. For instance, according to Kant, although knowledge starts with experimenting, it does not follow that knowledge is entirely derived from experimenting. In fact, without a prioris, that is, without a pre-established structure of the world, observation is meaningless because it does not come as a support of, or as a confrontation to, a referential model. Therefore, the building of knowledge through experimentation implies the existence of a prior representation system, which is very primitive at the beginning, but gets progressively actualized via these experiments. From this perspective, learning can be expressed as the critical examination of pre-existing external systems subjected to experiments, with respect to this overall referential representation of the world. The Bayesian approach is obviously in accordance with this perspective, since prior distributions are most often based on the results of previous experiments. Actually, even the subjective aspect of the choice of the prime distribution can be integrated in this theory of knowledge, since it implies that every acquisition of knowledge is essentially subjective, resulting from an interaction between individual perceptions and exterior reality. In his epistemological theory, Feyerabend also stresses that individualism, that is, subjectivity, is an important but blatantly ignored factor in scientific discoveries. Although opposed to this subjectivist approach to knowledge, Popper also recognizes the role of prior intuitions or systems, not always grounded on experiments, in the history of science, the most striking example being, from his point of view, atomism, that is, the representation of matter as being constituted by atoms, which took more than 20 centuries to ascertain experimentally. Personally, when I saw the devilish grin that the figure wore, I updated my prior towards the coin being biased against you. Your assignment is to prepare a 5-minute video essay in which you will share your personal thoughts about science. Right, so I think that what's interesting about this issue is